Welcome back to the Medicus of Houston channel and to this presentation of the mean QRS axis in the frontal plane. I'm Dr. Jerry W. Jones, the CEO and Chief Instructor at Medicus of Houston, and I will be your instructor for this video. Before we begin, let's clarify a few definitions so we're all on the same page. When I say right and left, I'm referring to the patient's right and left, not my right and left, but the patient's right and left as though they are standing there in front of you. When we're talking about the right upper quadrant of the heart, then we're talking about the patient's right side. If we're talking about the left lower quadrant of the heart, we're talking about the patient's left side. Now, the A with a little caret over it means the mean axis or average axis. You can have a mean P axis, you can have a mean QRS axis, or you can have a mean T axis. An isoelectric QRS will almost never be actually perfectly flat. You will usually see some deflections in this baseline. The deflections will likely be about 1 millimeter in height or depth. Now, an equiphasic QRS means that the area within the R wave equals the area within the S wave or Q wave. Let's take a brief look at the hexaxial reference grid. There it is. Now, the hexaxial reference grid includes all 6 leads from the frontal plane, but only the frontal plane. We don't have any precordial leads here. No leads V1 through V6. Just 1, 2, 3, AVR, AVL, and AVF. Now, a normal QRS axis in the frontal plane extends from plus 90 degrees all the way up to minus 30 degrees, from the lead axis of AVF to the lead axis of lead AVL. Now, it is not from plus 90 to 0 degrees. And it hasn't been since around 1968. So if someone is still teaching you that the normal QRS axis in the frontal plane is from plus 90 to 0 or 0 to plus 90, then you can see how long it's been since they've updated their knowledge. The mean QRS axis in the horizontal plane can certainly be determined, but we don't usually measure axis in the horizontal plane. We measure rotation. Now, the mean QRS axis in the horizontal plane can be calculated or determined. I did it many times, many years ago, but doing so is much more complex since leads V1 through V9 are not considered equally spaced. Now, to be perfectly honest, the leads in the frontal plane are not really equally spaced, but we can consider them so, and it works quite well. Not so much with the horizontal plane. Rotation tells us what we want to know. So in this video, we will be discussing the mean QRS axis in the frontal plane only. Determining the mean QRS axis in the frontal plane means taking thousands and thousands of depolarization vectors and finding the average. So how does that help you right now? It's certainly one of the first things you learn how to do when you start learning about electrocardiography, about interpreting ECGs. But how does it help you? Well, unless you're reading and interpreting ECGs at an intermediate to advanced level, it really doesn't. It doesn't. But don't get discouraged. It's teaching you a valuable bit of information and also skills that you will use as you advance. And you must advance because when someone's life is in your hands, introductory knowledge is simply not enough. Okay, so again, why doesn't the mean QRS axis in the frontal plane help you at this point. Okay, would you feel better about your patient if you knew the mean QRS axis was normal? It sounds like it should be good news, but it isn't really, and here's why. Almost all people with normal hearts have a normal mean QRS axis in the frontal plane. That's great, but so do most people with diseased hearts. See, knowing that your patient has a normal mean QRS axis really doesn't help. However, very, very few people with normal hearts will have an abnormal mean QRS axis in the frontal plane. So the mean axis is more informative if it's abnormal than if it is normal. Okay, let's get down to business. How do you determine the mean QRS axis in the frontal plane? Well, first you determine which lead is the most isoelectric or equiphasic. We'll get into that in just a moment. Then you find the lead that is located 90 degrees from that lead. That lead will represent the approximate mean QRS axis in the frontal plane. So how do I remember which leads are perpendicular to each other? Or how do you remember? It's like playing a game of tic-tac-toe. So we'll take a look at the next slide. Okay, here we have the 6 frontal plane leads arranged just as they're arranged on the ECG printout in most Western countries. It's a little bit different in some of the countries of Northern Europe, but most everywhere else you will see the frontal plane leads listed as 1, 2, 3, then following that AVR, AVL, AVF. So it's as though you're looking at the first portion of the 12-lead ECG right now. Okay, well, let's play a little game of tic-tac-toe and see what happens. We're going to create our first line and see what happens here. The lines connect all the perpendicular pairs. Here, let me illustrate that for you. Lead 3 is perpendicular to lead AVR. Lead 1 is perpendicular to lead AVF, and lead 2 is perpendicular to lead AVL. But why are we so interested in isoelectric or equiphasic QRS complexes? Let's talk a little bit now about vectors. Vectors that are parallel or angled with respect to the different lead axes. Now, any vector traveling parallel to a lead will inscribe the maximal deflection in that lead. Any vector traveling parallel to a lead inscribes the maximal deflection in that lead. But what happens when the impulse, or the vector, is traveling at an angle to a lead? Well, the angled vector leaves less shadow, shall we say, on the lead axis and a smaller deflection. Now, as you can see, as the vector becomes more and more vertical, less is directed towards the lead electrode, less shadow appears on that lead. When the vector becomes finally 90 degrees, there is no parallel vector. The lead electrode sees nothing, thus an isoelectric line. The deflection is still present. You can see it in other leads, and space for it will remain on the baseline, but you will not see a deflection for an impulse that is traveling at 90 degrees, traveling perpendicular to a lead axis. So why not just look for the largest QRS complex? That would seem to be faster and easier. Well, sometimes that works, but unfortunately, not always. Some leads may have QRS complexes in which the R waves or the S waves may appear somewhat misleading. The trigonometric relationship with its perpendicular lead can clarify a confusing situation. Let's say two leads have R waves that are tall and appear similar in size. Check each lead's perpendicular lead. The one with the least voltage will indicate the lead closest to the mean QRS axis. Here's a few more things to know about the mean QRS axis in the frontal plane. First, while an experienced electrocardiographer can usually determine the mean QRS axis in the frontal plane within just a few degrees, it isn't necessary at all. 95% of the time that I calculate the mean QRS axis, I simply want to know which quadrant it's located in. Again, the mean QRS axis is not a permanent finding. It can change from time to time. It becomes very important, however, in some cases of chamber enlargement, intraventricular blocks, myocardial infarctions, and ventricular tachycardias, just to name a few. Being able to detect smaller and more acute changes in the mean QRS axis in the frontal plane is often useful when diagnosing an acute cor pulmonale, that is, acute pulmonary embolus. Let's return now to the topic of an isoelectric or equiphasic QRS complex and talk about that for a little bit. Now, certainly isoelectric and equiphasic complexes don't look the same, do they? But they have one important characteristic in common. Now, here in lead AVF, we see a complex that almost meets both criteria. It's very, very small. The QRS complex, as you can see, is very, very small. It's not really isoelectric, but we can let the definition slide a little bit and say, okay, this is the most isoelectric of all the leads. And it looks like it could be equiphasic, as much deflection on top of the baseline as below it. So it's the most isoelectric appearing lead on this ECG and also appears to be equiphasic. Again, what do isoelectric and equiphasic have in common? Why are we looking for either one when they look so completely different? It's because they both represent zero net voltage or membrane potential. A nearly flat or isoelectric baseline represents zero net voltage. An equiphasic QRS represents zero net voltage because the area under the R wave equals the area under the S or Q wave, so the voltage of the two deflections equals zero. Okay, let's determine the mean QRS axis in the frontal plane for this ECG. Now, I'll get you started. You find the isoelectric or equiphasic lead. Well, that's going to be lead AVF. Now find the lead 90 degrees from that lead. Remember, it's time for our tic-tac-toe game. So the lead that is 90 degrees from AVF is lead 1. Since lead 1 is at 0 degrees on the hexaxial reference grid, the mean QRS axis in the frontal plane is around 0 degrees. The machine says it's plus 9 degrees, and that's certainly close enough. Well, that seemed to go well, so let's try this ECG, and I will help you with this one. Locate the most isoelectric or equiphasic lead in the frontal plane. I'll give you a moment. It's lead 3. Lead 3 has the most isoelectric appearing or equiphasic appearing QRS complex. Now the next step is, where is its perpendicular lead? Which lead is perpendicular to lead 3? Again, we go back to our tic-tac-toe game, and we see that lead AVR is perpendicular to lead 3. Now, lead AVR has a positive pole at minus 150 degrees on the hexaxial reference grid and a negative pole at plus 30 degrees on the hexaxial reference grid. So will the mean QRS axis be pointing towards the right upper or the left lower quadrant? Well, we can look in leads 1 and AVF. Leads 1 and AVF have QRS complexes that are upright. That alone tells us that the mean QRS axis is going to be located in the left lower quadrant. Now, don't get me wrong. I'm not saying that lead 1 and lead AVF constitute the boundaries of a normal QRS axis. They denote the boundaries of the left lower quadrant. So the axis would be at approximately plus 30 degrees, and the ECG printout says plus 35 degrees. So we got very, very close there. Very close. Always remember that sometimes the largest QRS is negative. Try this ECG yourself. Pause the video while you think about it. Where is the isoelectric or equiphasic lead? It's in lead AVL. Okay, which lead is perpendicular to lead AVL? Playing our tic-tac-toe game, lead 2 is perpendicular to lead AVL. So lead 2 is at plus 60 degrees, which makes the mean QRS axis in the frontal plane approximately plus 60 degrees. And the printout says that it's plus 65 degrees. So once again, we got very, very close when we only really needed to be in the same quadrant. Now, there's something very important to learn here. If you'll note that lead 2 constitutes the mean QRS axis in the frontal plane, it has the tallest R waves. And lead 2's lead axis is located at plus 60 degrees. What you need to understand is that most QRS complexes, most mean QRS axes in the frontal plane cluster around plus 60 degrees, right around the lead 2 axis. So when the lead 2 axis is acting as the mean QRS axis in the frontal plane, look what it does to lead AVL. Look at the QRS complex in lead AVL. It's almost indecipherable. It's extremely small. It's the closest thing we've seen to an isoelectric complex. Okay, imagine a little bit of ST elevation in lead AVL. Do you think you would notice that? Here's the question. Is the mean QRS axis in the frontal plane normal on this ECG? Pause the video for a few moments to study this, and then when you start it back up, we'll discuss it further. The answer is yes. The mean QRS axis in the frontal plane on this ECG is perfectly normal. It's absolutely normal. If you looked at leads 1 and 2 to determine this, you would have reached the correct answer. Had you looked at lead 1 and lead AVF, it would have told you that there is a left axis deviation, which is incorrect. If we want to determine if the mean QRS axis is lying within the normal range, we look at leads 1 and 2. We don't use AVF anymore for determining the limits of the normal range of the mean QRS axis in the frontal plane. Now, certainly looking at 1 and 2 does not tell us exactly where it is, but it tells us that it falls within the normal range within the left lower quadrant up to minus 30 degrees in the left upper quadrant. That is the normal range for the mean QRS axis in the frontal plane, and it's been that way since 1968. I want to take a moment to tell you about the courses in advanced electrocardiography that I teach. The master class in advanced electrocardiography deals with the advanced concepts that the intermediate to advanced electrocardiographer should understand and be familiar with. It's a live presentation. It's an in-person presentation. And it's very interactive. The classes are limited to just 20 participants. There are no auditoriums filled with 200 or 300 people. It's just you and up to 19 other people. Very much almost like a private session. You can ask questions at any time. You do not have to wait to the end of a session to ask a question. You can raise your hand and ask a question at any point during the lecture. It's perfectly all right. It's a casual, informal, and very friendly atmosphere, with most people calling each other by their first name. The curriculum is truly advanced. Now, this is not a review course. I reviewed a number of online advanced ECG courses and discovered that their curricula were pretty much the same as the basic courses. They were basically review courses. This is not a review course. You are going to be learning things you did not know. Now, each participant, everyone, actively analyzes complex ECGs in class with assistance from me. Everyone participates. I strongly believe that you learn by doing, not just observing. 28 AMA-PRA Category 1 credits are offered for the course. And there are generous group discounts starting with just 3 people. The San Antonio class will take place July 24th through the 27th of 2023 this summer. I certainly hope to see you there. Thank you so much for your time and attention. I appreciate it very much.